Hi, in this video, we're working in section 14.4. I'm going to go look over at the notes. We're going to be talking about a measure called the linear correlation coefficient. It's denoted by R, and it's a measure of the strength of the linear relationship between two quantitative variables. So I am actually going to jump down here to the examples and look at what R is. I know you're probably wondering, we just talked about the coefficient of determination R squared. Why are we talking about R? It seems, another measure of linearity, and they sound from their notation that they're related, and in fact, they are related. So if I had, and we'll go through going from R to R squared by taking that square or square root and how that works. But let's go ahead and think about the correlation. Linear correlation can be interpreted without really thinking about a regression model. We often think about the correlation between two variables. We don't necessarily have to have an underlying regression model to do that. The coefficient of determination is truly part of the linear regression analysis, okay? So it really has to do with how well the linear regression does at explaining the variability and why, where when we look over here at the linear correlation, we're really just looking at two variables and the measure of linearity between them. Okay, it doesn't necessarily require that we think there's a linear relationship, that we run a linear regression. It's just sort of two variables and how related they are in a linear manner. So the linear correlation coefficient is the measure of the strength of a linear relationship between two quantitative variables. We have properties, so we'll go through the properties. But first, let's just look at what the linear correlation coefficient looks like. If the data is perfectly laid out on a straight line, the X and the Y are, their scatter plot lie exactly on a straight line, then that is going to give us the largest correlation, linear correlation, and it's going to be R is equal to 1. And if the data is perfectly laid out on a straight line, the scatter plot looks like a perfect straight line, then R is equal to -1, and that's going to be the lowest value. So both of these are strong, maximum positive correlation and minimum negative correlation, right? So these are the strongest correlations. And then here in the middle, we have a cloud-like situation where the correlation is 0. That is to mean that the X and the Y, there is no linear correlation between X and Y here in this picture on the where the 0 correlation, R equals 0. So we have two intermediate situations worth looking at here. So we have this one, the strong positive correlation where R is equal to 0.8. We see that as X increases, Y tends to increase, but the data points are not lying on a straight line. And the moderate negative correlation, R equals -0.43. In this picture, the data is negatively correlated. As X increases, Y tends to decrease. It's more spread out than the graph right above it, which had a 0.8 linear correlation. All right. And then over here, we have an interesting thing where we see that the data pretty much falls on a straight line except for this one point. So this gives us an R of 0.71. This gives us an R of 0.71. And over here, if we didn't look at the graph and we just asked for the numerical, we asked our software system to just report to us what the correlation coefficient was, we might think that we were in a situation similar to this positive strong correlation, but in fact, we're really not. We really have one outlier and points that are perfectly correlated. So this is sort of the moral over here is you have to look at your scatter plots when you're playing with data. You have to look, okay? All right, so let's go back up here and look at some of these properties. Correlation coefficient doesn't depend on the units. So if you're measuring distance in feet, inches, it doesn't matter. If you're measuring temperature, it doesn't matter what unit you use to measure your variables in. This is a unitless measure. It's always between -1 and +1, right? So it's all correlation coefficient is always between -1 and +1. And positive values of R correspond to positive relations between the X and the Y variable. Negative values of R correspond to that negative relationship. One increases, the other decreases. Okay. We see that when R is +1, that is a strong positive relationship and the points are really on a straight line. If R is -1, it's a very strong negative relationship because the points do fall on this straight line. When R is closer to 0, we have less of a linear relationship. Excuse me. The data looks cloud-like. So if it's close to 0, there's less of a relationship, even if it's a little bit positive, a little bit negative, like -0.01 or plus 0.01. It's still going to be like cloud-like and really be interpreted as no linear relationship between the variables. Okay, so I guess there are several points from the scatter plots. I think that the slope, when the slope of the regression line in the plot is negative, then the correlation coefficient is going to be negative and vice versa, right? So the strongest relations are +1 and -1. That in those situations, the data falls on a straight line. The correlation becomes weaker as the data points become more scattered. And if the data points are random, then the correlation is either equal to or close to, if the data points are cloud-like, then the linear correlation coefficient is equal to or close to 0. And correlation can be affected by outliers. All right, so looking back up at these pictures, I do want to take a minute and discuss the relationship between the correlation coefficient that we're studying in this section and the coefficient of determination that we studied in the previous section. So I put a couple of these graphs up on the whiteboard. We'll go over there for a moment. And of course, I didn't really put them up exactly on the whiteboard, but you get the point. So I'm looking at the first up on the left, and we have this R of +1. So R squared is going to be the square of the correlation coefficient. So the coefficient of determination is the linear correlation coefficient squared. So in this case, +1 squared. That correlation coefficient, that coefficient of determination is 1, but coefficients of determination are presented as percents. So while we call R1, R squared is going to be 100%. Usually how these are communicated, right, in percents, coefficients of determination, because it's the percent of the variability in the Y data that's explained by the X data. Okay, and over here, we have R is equal to -1. So again, R squared, we're going to square the R, which is going to be 1. And again, so we see the coefficient of determination is 100% in both of these situations. So we're going to go over and look at these more moderate situations. and calculate the coefficient of determination. So we'll need the calculator. So R squared is going to be 0.8 plus 0.8 squared. And we get 0.64, which is 64%. And then finally, we're going to come down here to this negative correlation, and we're going to figure out what R squared is. Okay, so R squared is equal to negative 0.43 squared, and that's going to be I'm a little slow with this. This is 0.1849 or 18.49%. Okay, so you can begin to see the relationship between the R linear correlation and the coefficient of determination R squared. I'd like to also be able to go in the other direction. So hold on one second and let's come back to the notes. I'm going to go back to the scatter plots that we looked at in the previous section, and we're just going to find so we're given here in this picture here, this is the mom and dad heights and my students' heights, and we're given that R squared is 74.8%, and I want to be able to translate that to transform that into a linear correlation coefficient. All right, so I just transferred the information we need over here to the whiteboard. Y is equal to, and rounding to one decimal place, minus 5 plus 0.5x, and the R squared is 74.8%. So to calculate the linear correlation coefficient from this information, R is going to be plus or minus, and that's going to come from the sign of my slope, but plus or minus the square root of R squared. R squared is always positive, so we'll always be able to do that. And then after we take that square root, we're going to choose either a positive or a negative sign, depending on the sign of the slope there, or if you look at the scatter plot, you can determine that by just observing whether there is the Y data tends to increase as the X data increases. Okay, so what we're going to do here in this case, and we have to change this to a decimal point to do the math. So we're going to put that in here, 0.748. So we're going to take the square root of 0.748. And we get R is equal to plus or minus 0.86. And now we need to choose the correct sign. And so the correct sign is plus and not negative. So my correlation coefficient is 0.86. Okay, we'll do another one too. So let me look back at another one of the pictures. Okay, so I'm looking at another one of the graphs here. And this is the energy and tax efficiency graph, and we had the data which has a negative slope. The regression line has a negative slope, and R squared is given as 95%. So we're going to go over to the whiteboard and calculate the linear correlation coefficient. All right. So I put on the whiteboard the regression equation. I can see that there's a negative in that the slope has a negative sign. And that r squared is 0.95, or I'm sorry, r squared is 95%. So the first thing we have to do is translate that to a decimal, and then we calculate r, which is going to be plus or minus the square root of r squared. So r is going to be plus or minus the square root of 0.95. And I'm getting 0.97. So then r is going to be plus or minus 0.97. And in this case, because the data is has a negative, I'm sorry, the regression line has a negative slope, we're going to go with the negative sign. So my r is minus 0.97. That's my linear correlation coefficient for the data presented in the graph over here. Okay, so I think there's a little wrap up I wanted to go through at the end that sort of just gives probably most of the points we've already shared, but worth kind of saying it again. When the slope of a line in the plot is negative, then the correlation is negative. When the slope is positive, the correlation is positive. -1 and +1 are the strongest linear correlations. That's when the data falls exactly on the line. The data becomes weaker as the data points become more scattered. I'm sorry, the correlation becomes weaker. Data doesn't become weaker. Correlation becomes weaker as the data points become more scattered. And if the data points fall in a random pattern, like a cloud, then the correlation is close to 0 or equal to 0. And correlation is affected by outliers. So you should compare, you should always look at your scatter plot before you report your linear correlation coefficient, just so you know what's going on. This is a picture of the data we worked on earlier in the chapter, number of absences and average grade. Okay, and just so you, this is from the software system SPSS, and you can see here that this is how they report the linear correlation. They don't, software systems can do what they want to do as long as they document it. So in fact, here we get this value of R, but it is unsigned. We have to add that sign ourselves. So in this data here, R is negative the linear correlation is negative, and it's 0.947. And the R squared is 0.898 or 89.8%. All right. So that's it for this section, and I'll see you in class.